organizers for the invitation. It's a pleasure and an honor to be here. So I would like to discuss fund foliation. So this is actually I will explain some of the results that I have been developing in a series of papers with my collaborator, Stefan Druel. And what we are doing is we are exploring some strong connections between birational geometry over the complex, so in particular MMP, and the theory of holomorphic foliations. So which I will refer to just as foliations. So these connections have some long history, and I will try to tell you a little bit about that. So before I do so, I will assume that most of you are familiar with birational geometry, but not so much with foliations. So let me start by defining what a foliation is. So we always be working on X, a smooth projective variety, complex projective variety. So even though some of our results hold for, we have developed some theory for singular varieties as well. So let me start by defining what foliation is. So foliation on X is a non-zero coherent sheaf of the tangent bundle proper coherent subsheaf of the tangent bundle subject to the following conditions. So first, so this is what is called the integrability condition, or the Frobenius condition, that says that F is closed under the Lie bracket, and the saturation condition, which says that F of Tx over X is torsion free. So let me briefly explain what these conditions mean. So tangent sheaf of the subsheaf of the tangent bundle, you can think of this as for every point of X, I give you say a linear subspace of the tangent space of the proper dimension of the generic rank here is R. And the integrability condition is telling us that in fact you can integrate this distribution. In other words, it said that if I take a point X outside the singular locus of the foliation, so the singular locus is just the locus where this is not an inclusion of vector bundles. So at a singular point, at the general point, a non-singular point, there is some analytic neighborhood and a product structure. So there's going to be some U, so here is an analytic neighborhood, and some product structure, a map, a smooth morphism to some analytic space V, such that our F in this neighborhood is nothing but the relative tangent to this map. So this is what integrability condition is telling you, is that you, so here the planes actually come from tangent spaces to these fibers. And then you can, of course, do some analytic continuation. So if you take other open sets, you can sort of extend these fibers. And if you take a maximal connected component, you get what we call a leaf of the foliation. So if you take maximal connected component, that's what we call a leaf of F. So this is about the integrability condition. Now for the saturation, so this is because we are going to be using, we are going to be computing, for instance, the Chern class of F. And here, of course, you could have two subsheaves that coincide in some open subset. So they are defining the same geometry. And so what we do is we take it we saturate it inside the tangent space so that there is a unique representative. So this is this condition here. So it will make sense to talk, for example, about the first term class. That's what we are going to do next. Okay, so let me just give you some examples of foliation. So for us, for algebraic geometers, the most natural example is the ones that come from rational maps. So if I have a dominant rational map from X, so we use this to denote dominant rational map. So if I have a dominant rational map, I can restrict to the open subset where this is a smooth morphism. I take the relative tangent, and then I saturate it in X. So this is what we call, let me write it simply this way. So this is a foliation, the relative tangent to a rational map. So this is very nice because here the leaves are just algebraic varieties. So this is what we call an algebraic foliation. Now, of course, not every foliation is algebraic. So the easiest example of non-algebraic foliation is if you take, in PM, if you take a global vector field, so there are plenty of vector fields, and once you have a vector field, you get a foliation by curves induced by this vector field. So this is just going to be OPN inside the tangent bubble. And if you choose your V general, then the general leaf is going to be transcendental. So this is what we call a totally transcendental foliation. So that means that through a total transcendental foliation would be one for which, for a general point, there is no algebraic subvariety that is tangent to this foliation. And of course, here in general, what you have is you have a mixed behavior. So you could take, for instance, a map, a dominant rational map to Y. You could have a foliation G on Y. Say it totally, so it could be this one, totally transcendental foliation. And you can define a foliation F to be what we call the pullback of G. So this is just the inverse image by the differential of G. So here we have an algebraic, in this case we would have an algebraic part which comes from the rational map and a totally transcendental part coming from this foliation on Y. So in general, given any foliation, you can construct a map of this type, separating the algebraic part from the totally transcendental part. So these are some examples, and now maybe I want to define the main object.
So totally transcendental means you don't have any subvariety such that the tangent value is contained in the
right, through a general point.
Possibly of lower dimension.
Through special points. Through special points you can have algebraic subvarieties tangent to the foliation, but through a general point there isn't a single algebraic curve that is tangent to the foliation.
Yeah, if I take I mean maybe this is a crazy question, but if I mean this H naught is just a finite dimensional vector space.
Right.
What if I look at the set of all V's that give me totally transcendental things?
Yeah, this is an open subset.
Classically open, I assume.
Yes.
Or is Zariski open? But if I look at the things that are not totally transcendental, is that wild?
No, I don't know, but yeah, I believe that this would be a closed subset.
Zariski closed.
Yeah. But I'm not sure, this is my guess.
Sorry, in
Yes.
number 2, say what a leaf of that foliation would look like?
That's what this is integrating the vector field. So this, I mean, this is not an algebraic curve. It's an analytic curve of dimension 1.
It's a virtual Lie subgroup.
Right. Yes.
It's exponentiated.
Right. Exactly. Okay. So let me then define what a funnel foliation means. So we will now we'll start defining invariants of the foliation. So the first one is what we call the canonical class of the foliation, which is just as you do for the tangent bundle. So this is minus the first Chern class of F. And we say that, so this is the canonical class, and we say that F is Fano, the Fano foliation, if the anticanonical class is ample. And as in the case of Fano manifolds, we can define the index of a Fano manifold. Here we can do the same thing. We can define the index of a Fano foliation to be the largest integer such that the anticanonical class writes as m times some ample line bundle. And here, let me just give you we are going to talk in more details about this soon, but I just want to give you a preview of some properties, special properties of Fano foliation. So if you were here for Ana Maria's talk yesterday, you learned that a Fano manifold is rationally connected. So here we have a very similar property. So if you have F, if F is a Fano foliation, there exists some subfoliation G. So some that is algebraic and whose leaves are rationally connected. So there exists some algebraic subfoliation with rationally connected leaves. So I will discuss this later on. And the sort of the philosophy or the rough idea that I want to express is that the highest is the index, the highest is the rank of this subfoliation G. So when the index is very high, X will have to tend to be very algebraic. Okay, so now maybe I should say a little bit about the theory of homomorphic foliation. So that started in the 19th century with works of Poincaré and Barabou. So they were interested in studying solutions to first order differential equations. And so they were interested in understanding local behaviors of the solution. So the solutions come as exactly as foliations. Later on, right in the 20th century, people started to look at foliations from an algebraic geometric point of view and started to be more interested also in global aspects and modelized spaces and so on. And I think for me the striking thing comes in the early 21st century when people started to be interested in classifying foliations, in developing a birational classification of foliations. So McQuillan and Brunella worked a lot on that, and I think that culminated with Brunella's classification of foliations by curves on surfaces. So he had a classification that is very much similar to the classification of algebraic surfaces, and that is based on the behavior and the sign of the canonical class. Yes?
Sorry, can I ask? So if you have a Fano foliation, is it algebraic in the sense that the leaves are all algebraic?
Not always. I will give some examples. Not always, but what I'm saying is that there is some subfoliation which is algebraic, some non-zero here, some non-zero foliation that has algebraic and rationally connected leaves. And if I increase, if the index is high, we will see that this rank here is increasing. But we will see an example of a Fano foliation which is not algebraic. Just wait a bit more and we will get there.
Okay, and by algebraic foliation, it means that the leaves are actually algebraic also?
Exactly, the leaves are algebraic. So that means that it comes from a rational map of algebraic varieties.
Every leaves or general leaves?
So if the general leaf is algebraic, then the special leaf will have to be algebraic as well. Okay, so this is from the point of view of holomorphic foliation. So people now are using techniques from the minimal model program and classification of surfaces to study, to give a birational classification of foliation by curves on surfaces. But now, if you're an algebraic geometer, you may say, okay, so why should I care about foliation? So I would like to give a motivation example of how foliations appear in purely algebraic geometric problems. So let me give you some motivation. Okay, so this is actually one of my favorite open problems in algebraic geometry, which is the stability of Fano manifolds with Picard number 1. So there is this conjecture which, as far as I know, goes back to Tskowski. I hope I write this down right. Which says that if you have a Fano manifold with Picard number 1, then the tangent bundle of X is stable. So this is an open problem, and that there are some instances that are known, but in general this is wide open. And let's see how foliations come into this picture. So let's assume that that the tangent bundle is not stable. Okay, so first of all, let me just remind you what is the stability condition in this case. Since the Picard number is 1, let me define the slope in this case. If I have a torsion-free sheet on X, I can define so its determinant is going to be a line bundle, so it will be here the peak. It's generated by manifold A. So the determinant is going to be A to the power, some power, which I will call the index of the sheet E. And the slope is just the index divided by the rank. And to say that it is stable, it means that any subsheet of the tangent bundle must have a smaller slope than Tx. So what happens if Tx is not stable? Well, then we can take what we say, using the Harden or Riemann filtration, you can construct what we call a maximal destabilizing subsheaf, which I will call F. And while this has several properties, so what does that mean? So from one side, of course, this means that the slope of F is greater than the slope of the tangent bundle. Now this one here is just the index of F divided by the rank. This one here is just the index of X divided by the dimension N. And see what this is, and what we see is that the index must be very large compared to the rank for such destabilizing subsheaf. But moreover, this is not only any subsheaf. So the properties of the maximal destabilizing subsheaf tell us that in fact this is a foliation. So it's not difficult to check that from the construction of F, the home of F to F, sorry, Tx mod F, this has to be 0. So this is saying that it is closed under the Lie bracket. So F is in fact is a fundal foliation with sort of high index compared to the rank and to the slope of X. So this is one reason why you may want to study fund foliations. And I should say that I don't think this tool has been much studied in this problem. So there is some hope that we can use this to approach this conjecture. Okay, so our goal then is going to be try to understand, to say something about fundal foliations with high index. So the first natural question that comes is that, okay, so how big, how large can the index be? So let me just describe an example. What happens in the case, the easiest case, the case of Pn? So what happens when X is equal to Pn? So we have here foliation on Pn. So if you, so this means that you have, if you take so this has rank R. If I take the R wedge power, what I get is a section of the R wedge power of TPN twisted by KF. And now here we have, so this is going to be just minus index of F. And here we have a box formula which tell us what are all these cohomology groups. So from box formula, you see easily that in this case the index must be less or equal, here this is a proper subsheaf, so this has to be less or equal than the rank for Pn. So this is just an easy computation. Okay, so what happens in the extreme cases? So let's see. So again, here we are in the case when X is Pn, and we have just seen from box formula that the index F is a fundal foliation in Pn. And we have just seen from box formula that the index has to be at most equal to the rank. Now this extreme case has been classified. Yes?
Can you raise the board
Mine's broken.
It is broken, sorry.
Oh, it's broken. Okay.
I will raise this as soon as I finish writing. Okay, so let me just talk about the extreme case. So this has been proved by, so this was a theorem of Araujo. This is 2006. They proved that in this case, so if the index is equal to the rank, then in fact, this is a very, very simple foliation. So this F must be O1 to the power r, that means that this f is induced by a linear projection. So i.e. f is induced by a linear projection from Pn to Pn minus r. So that means that you have to fix an r minus 1 dimensional linear subspace, and you're looking at all linear subspaces of dimension r that contain this fixed Pr minus 1. So this is the foliation we are talking about. Now the next case has also been classified, which is when the index is r minus 1. So this is a theorem of Logue, Pereira, Zé, from 2011. And what they show is that if the index is the next possible value, r minus 1, then there are two cases. So the first case is algebraic. So this case, of course, is algebraic. So the first case is also algebraic. So f is induced by a rational map from Pn to a weighted projective space, weights 1 and 2. So that means that it's given by a bunch of actually n minus r linear forms and not one quadratic form. So you see that the leaves in this case are r-dimensional quadrics. So this is algebraic. And the second type is the following. So there exists again a linear projection. So linear projection to Pn minus r plus 1. And a vector field here, and a vector field in this projective space. Such that our f is the pullback via phi of the foliation by curves defined by this vector field. So it's easy to check, to compute the canonical class in this case, and you get that the index is exactly r minus 1. So now here I want to emphasize that, as we saw before, if I take a general vector field, this is not going to be algebraic. So in this case here, f is not algebraic.
Can't read blue.
Sorry?
Can't see blue.
Oh, okay. Red is okay, or? I'll write it in white. Okay. In this case, f is not algebraic.
Wait, so is the conductor known for Pn? Are you using that to roll?
Sorry?
Is the conductor known for Pn? Is that how
Yeah, the conjecture is known for Pn. For Pn, for complete intersection. So there are some classes of varieties for which it is known. But this is sort of follows as a consequence also of this computation, that the index is at least knows the rank.
Wait, so how do you know an index is less than r? It's because you know the conductor, or you know?
Because of this.
Oh.
So this is just you construct, or you can think of this as a twisted differential form on Pn, and then you just use Bott's formula, which give you all this homology groups.
And each foliation arises like this?
Yes, because see, you just take a wedge power, an arc wedge power, and then this is exactly what you get if you work it out.
So the superscript R right there, right?
This is the rank.
Ah, that's right.
Yes.
Is the conjecture viscosity known for smooth funnel people?
For funnel threefolds, it's okay.
It's not.
It's not. Yes, you can check in the list one by one. Okay, so let me start by then telling some of the, let's go back now to the general case. Let's see. Okay, let's now go back to the general case. So for Pn, we can easily show that the index is at most the rank. And of course, you expect that Pn is the variety which has most positive tangent bundles. So once you have this bound for Pn, you expect it to be true in general, and in fact, it is. So this is so this is a theorem that I proved with Stepan Puel and Szymon Kovac. In 2008. That says that in general, if for X monofiliation on any smooth projective variety X, then the index of F is at most the rank. And if equality holds, then we are in the case when X is Pn. Okay, so this is the theorem, and now what I will define is, okay, now we want to look at the next cases. So just as in the case of Fano, so this should be viewed as an analog of Kobayashi-Ochai theorem that Ana Maria proved yesterday. So the index is bounded by R, and if equality holds, we are in the case of P1. So now I will define F to be a del Peso foliation if the index is equal to R minus 1. And I can define a Mukai, again, foliation if the index is 1 less. And our aim would be, say, to classify monofoliations with high rank. So let's first look at the del Peso case. So what can we say about del Peso foliations? So here let me give some results about del Peso. Theorem that I want to describe is concerned with algebraic integrability. So as I pointed out here, we just saw an example, a very simple example of a del Peso foliation which is not algebraic. But our first theorem says that this is the only case. So if F is a del Peso foliation on a variety different than Pn, then F is algebraic. And moreover, leaves are rationally connected. Okay, so this is the first result, and then I hope I will have time to also, let me just state this. Or maybe just for the moment just say that our next, so this is our first result, and then our next result give some classifications of del peso foliations under some conditions. So before I state this, maybe it's time to give some more examples. So this was the case of PN. Now you could ask, okay, so what is the next simplest case? Well, this would be the case of a quadric hypersurface in Pn plus 1. So can you find del peso foliations on a quadric? And the answer is yes. And we have classified them. So in fact, this F del peso foliation on a quadric must be of the following form. So F must be induced by a linear projection from Pn plus 1. So this is Pn plus 1. So F is induced by a linear projection from Pn minus 1 to Pn minus R. Pn plus 1 linear projection. Okay, then you can ask, okay, what about, say, cubic hypersurfaces or higher degree hypersurfaces? So let me just make a remark here. So if the degree of the hypersurface is small, you can still find foliations, but the larger the degree, the smaller the index is going to be. So to be precise, if I have F of rank R, foliation on a smooth hypersurface of degree D in Pn plus 1, then an easy computation of homology groups shows that, in fact, the index of the foliation must be at most R plus 1 minus D. And this upper bound is attained exactly by the ones given by restriction of linear projections. Okay, so maybe now I can at least state one of our classification results. So, say theorem B gives a classification of codimension 1, that means rank n minus 1, del peso foliations. So if the Picard number is 1, then if there is a del peso foliation on X, then either X is Pn or the quadric, and then the foliation is given on those boards. And if the Picard number is at least true, then this must be, X must be a projective space bundle over P1. So, so X must be projective space bundle over P1. Here we classified all the possibilities for E. So let me just say that E
Over P1.
is, I'm not sure if I should do this, but okay. There is a list. In this case is A, some positive integer, and there is one last case. So in this case, so only for those projective space bundles over P1 you can have a del peso foliation. So this is, in particular, see that the dimension of X is either 3 or 4. And moreover, in this case, we actually do get a description of such foliations. So these are given by, say, linear projections from PE to PK. So K is some rank 2 subbundle of E. And here you have a foliation by curves whose determinant we understand. So here there's a foliation by curves. And our F is just the pullback of this foliation. So this is a complete classification. I'm not sure if I will have time to state this, so let me just say that we have other theorems. So for instance, this theorem here in fact holds for possibly singular x, but now there will be some more cases here. And we also have a result for arbitrary rank, but we have to impose restrictions on the singularity of the foliation. So I hope I will talk about the singularities of foliations soon, but at this moment let me just leave these two results. And I would like to sorry, this?
No, I mean the back feet.
So this is just a relative linear projection. So K is a subbundle of E, and then when you have a subbundle of E, you get an induced relative linear projection.
Oh.
So this is sort of similar to what's happening in this case here, but over a base C. Okay, so I would like to at least sketch the proof of theorem A. So let me start by saying what are the key ingredients of the proof of theorem A. So let's say there are three key ingredients. So ingredient 1 is a very useful theorem to prove algebraic integrability. So in a sense, it's the only, or the strongest criterion that we have to prove algebraic integrability. So this is by theorem by Bogomolov, by Quillen. And I should say that also this goes back to the algebraic part is due to Boss. So the criterion says the following. So if you have a curve C, a proper curve, contained in X, avoiding the singular locus of the foliation. So if this is a curve, so if C is a curve such that the restriction of F to C is an ample vector bundle, then the leaf of F through a general point of X, of C, is algebraic and rationally connected. So let me tell you, for instance, how this ingredient proves theorem A in the case of card number 1. So maybe I should write this as a corollary. So as a corollary, you see that if I have a funnel foliation or actually semi-stable, then F is algebraic and the leaves, or the general leaf, is ration connected. And why is that? Because, well, here we use method of Manhattan theorem that says that if F is semi-stable, then the restriction to a very general complete intersection curve is also semi-stable. But because F is funnel, it has positive degrees. So in particular, this is a theorem of Hartree. This is an ample vector bundle. So in this case, we know that then all the curves, all the leaves are algebraic and rational connected. And now let's see how this gives us the proof of theorem A when the Picard number is 1. Okay, so if F is semi-stable, then okay, then the theorem, the corollary tells us that it is algebraic with rational connected leaves. Now, if not, we can take G, destabilizing subsheaf. So what does that mean? So we have that the index of G, so this is a proper subsheaf over the rank G, is greater or equal than the index of F over the rank of F. But this is, by assumptions, this is a del peso, so this is R minus 1 over R. And this has to be less than R. So we get that the index of G must be at least equal to the rank. But then we have seen that this implies, by the Kobayashi-Oshai for foliations, that X is isomorphic Pn. So this is a contradiction. So this gives us the proof in the case of Picard number 1. Okay, so this was the first ingredient. Now the second ingredient is, I would say, is the theory of rational curves on varieties. So ingredient 2, the theory of rational curves on varieties. So I will say how rational curves enter the picture in more detail soon. But first I would like to describe the third ingredient. And this is somehow, this is a sort of a new object that showed to be very powerful in our study of foliation. So this is what we call the log leaf. So what is the log leaf? So let's say that F is an algebraic foliation with general leaf F. So here by leaf, I'm taking the closure of the leaf in the algebraic case. So I have this F. I take the normalization of F. And it turns out that there exists sort of canonically defined Weyl divisor in F tilde with the property that the canonical class of F tilde plus delta is just a pullback of the canonical class of the foliation. So this is sort of why we call it the log leaf. So this is what we call, so F, this pair is what we call a log leaf, or a general log leaf of F. And we use the log leaf to define notions of singularities for foliation. So we say, for instance, that a foliation is log canonical along the general leaf if the general log leaf is log canonical. So we say that an algebraic foliation is log canonical. Let me just say log canonical for this talk. So it's log canonical if the general log leaf, as I just defined, is log canonical. And this is actually what allows us to use all the techniques from the minimal model program applied to this pair to study foliations. So for instance, let me state a proposition. So this is it's a very important feature of sort of mild funnel foliations. Oh, sorry. So if I have this, so the proposition says the following. So if F is an algebraic log canonical funnel foliation, then there is a common point in every leaf. Then there exists a common point in every leaf. So let me give you an example. So, okay, so this is one example. So in Pn, so here in Pn, this foliation with index equal to the rank. So you see that what is the log leaf in this case? So the log leaf F tilde is just PR, and the delta is just a linear PR minus 1. So this is the delta, the log leaf in this case. Of course it is log canonical, and in this case you see that you don't have only one point in every leaf, or the closure of the leaf, but every point here in this PR minus 1 is contained in the closure of every leaf. So I should say that I stated this, there is a common point, but we can actually prove something stronger. There is in fact a common log canonical center in the closure of every leaf. So for those that know what that is. And let me point out that the condition, that log canonical condition is necessary. So let me give you an example of so I find it very, very nice foliation. So this is now here, X is going to be the Grassmannian of lines in Pn. So so here is the Grassmannian of lines in Pn. So let me just draw Pn. And I will describe a foliation F. So this is going to be a deltezo of rank 2, defined in this Grassmannian. So what we do is the following. So I will describe the leaves. So you fix a point in Pn, X, and I will tell you what is the leaf of the foliation at a general point L. So L, a point in the Grassmannian, gives you a line in Pn. And let's look at the P2 generated by this line and the point X. So here you have a P2 of lines in this plane, and this is the leaf. So if you take a general, if you notice that there is each point is contained in a unique leaf, except the points corresponding to the lines through the fixed point x. So in this case, what is the log leaf? So the log leaf, the f tilde is just P2. It's just the P2 of lines contained in this plane. The delta is always supported in the singular locus. So in this case here, the singular locus is the line of lines through x. So this is just a linear P1. So this is the delta. So this is call it H. But if you compute the canonical class, you see actually that delta is 2 times H. So set theoretically it's just a singular locus, but here we have this multiplicity. And in fact, if you take 2 general lines in Pn, if n is at least in 4, the 2 leaves will not meet. So this existence of a point in the closure of every leaf really needs this condition here, the log canonical condition. Okay, I guess I don't have much time, so if I have, can I have 5 minutes more? So I would like to sketch, now that I gave you the ingredients, I would like to sketch the proof. Sorry, maybe I can break this.
Is there a canonical way to construct the F tilde?
So the F tilde could be quite singular, in fact. It's just normal, but it's difficult in principle to know what F tilde can be.
I wasn't just sure whether F tilde is something that you just cook out of.
Sorry?
I wasn't so sure whether F tilde is something that you cook out of.
This is F is a leaf. Is a leaf of a general leaf of the foliation. F tilde is just the normalization of F. So now let me just sketch very quickly the proof of theorem A when the Picard number is at least 2. Okay. Okay, so first of all, we notice that X is uniruled. Just because if F is semi-stable, again, you know that it's algebraically rationally connected with rationally connected leaves. If not, we can always find a maximum destabilizing subsheaf, which will be algebraically rationally connected leaves. So in any case, X is always uniruled. So we fix W, a minimal covering family rational curves on X. And we would like to understand the behavior of the foliation with respect to this family. So once we fix this, let's look at the rationally connected quotient with respect to this family. So this is the H rationally connected quotient. So what that means is that this is a proper map, a proper morphism defined on some open subset of X, with the property that the fibers of these morphisms are precisely the equivalence classes of points that can be connected by curves in Y. So this is the definition of the rationally connected quotient. So we see that if we will compare F with this rationally connected quotient, so if F is contained in the relative tangent, then okay, we use induction. So from here it's not difficult to conclude. Now if not, then we will see that we will intersect F with the relative tangent, and then we will try to understand this subfoliation. So what happens when you, let me call here general fiber XY. So what happens, so F then in this case induces foliation of smaller rank Fy on xy. And let's see what this foliation should look like. So we know that the pullback, so the restriction of Tx to a general member of the family, we know that it is of this form. And moreover, so here maybe I can write this here, so we have this exact sequence. So here we have the F. And the quotient, so the fiber has trivial normal bundle, so we see that this part here, that our foliation F is contained in here, and in most cases, because we know that the degree of F is R minus 1, or that the index is R minus 1, in most cases, this is going to be of this form. Now, this part here must be contained in the fiber, because this part here, the normal bundle of the fiber is trivial. So what we see is that the restriction, what I'm trying to say is that this foliation induced on the fiber must have rank R minus 1. So the foliation F on xy has rank R minus 1 and index also R minus 1. Because all the positivity must stay on the fiber. So that means that from the Kobayashi-Shaitan foliation, that means that this must be equal to Pn, and this Fy is just the foliation induced by a linear projection. Which in particular, we know that this one is log canonical. And then, okay, maybe I'm not going to extend on that, but see, here we have the F, here we can intersect and get a G here, and here we're going to have some quotient with degree 0 with respect to the fiber, so this will have to be pullback of some C, so we get some foliation by curves on the base, and a foliation on the fibers. The ones on the fibers, this G here, we know that it's log canonical, and we know that the leaves do not have a common point. So, this G cannot be funnel because of our proposition. If it is funnel and log canonical, it would have to contain a common point in the leaves. So because it is not funnel, you see that, okay, so this is just to sort of tell you that this gives you a hope that there is positivity left for C for us to apply again Bogomolov, McQuillan, Bost to conclude that this foliation here is algebraic, the leaves are rational curves, and then sort of show that this is actually glued together and our foliation F is in fact algebraically. Okay, so I'm sorry for this hurry in the end, but I guess I'll just stop. Thank you.
Thank you very much. Are there any questions?
Is there any kind of vanishing theory for the canonical division of foliation?
Yes, we do use, especially in the singular case, where theory of rational curves that don't apply so well, we do use some vanishing theorem. So maybe one vanishing theorem that I prove is that for x, under some restrictions on the singularity of x, we show, but this is vanishing for the H naught. So this is that if you have a funnel foliation, then this thing must vanish. Let's see if I get this right. So we do get vanishings of this of this type. And here I think we can assume that X is, well, we do have some restriction on X, maybe like terminal, but I'm not quite remember right now.
Any other questions? All right, if not, thank you very much again.